Okay, so today we want to talk about, begin talking about uniqueness and stability. And I'm going to focus specifically on net stress work and net complementary stress work today. And I know those terms might be unfamiliar to you, so don't panic. We'll talk about what that means. But it sort of in a high level summary, what we want to start doing is restricting the kind of material behavior that we want to work with, and then talk about how those restrictions manifest themselves in terms of things like energy, for example. So let's write that down, that we want to restrict material behavior now in a specific manner. Okay, so what do I mean by that? I mean that if we were to draw a stress-strain curve, right, so I'm going to now say this is just epsilon ij, right, so it could be any of those stresses, strains, sigma ij, that we have, let's say, initial elastic load up, and then we could have a material that does this, right? We'll call this type of material a hat, and then alternatively we could have a material that does something like this. We'll call that material A. And our goal here is we want to exclude materials that behave like a hat. Why? Because a hat is unstable. Okay, so what does that mean? If I have load control and I pull on it with a fixed load, once I cross this point, if I keep the load fixed, basically I will strain to as far as it can strain until it goes to, I rip it into two pieces, but there's not an equilibrium solution. So what I mean by this is that under load control, when E tan is less than 0, right? So when we have a negative tangent modulus, an increment of stress gives an uncontrolled strain. Okay? So that's what we're trying to eliminate. We need to know what sort of criterion would eliminate that class of material generally. So instead, we want to study materials that behave like A. So what distinguishes A from A hat in this case? I mean, what you could say is that the A hat has some component where the tangent modulus is less than 0, so a negative tangent modulus. But we typically write this in terms of the product of the stress increment and the strain increment that it gives. And so we'll say that the characteristic that distinguishes the difference is that for A, we can write that d sigma ij, the increment in stress, d epsilon ij, and the corresponding increment in strain, is greater than or equal to 0 for all d sigma ij increments in stress. Okay? So this is equivalent to saying that we have a positive tangent modulus, right? It says that sigma, the increment in stress, the increment in strain have to have the same sign, right? So let's go ahead and we'll call that equation 1. Okay, so now we're going to talk about a specific type of loading. And we want the loading to be a monotonically increasing stress. So we restrict loading to be a monotonically increasing stress. So what is that? What do I mean by that? Well, if I'm going to draw now what my loading is going to look like in stress space. So this is just sigma ij and maybe some other sigma ij. So maybe this could be sigma 1, 1, and this could be sigma 1, 2. So it's some ratio of stress to normal strain or something like that. But the point is that we have some point in stress space. We'll call that point A. And we're going to move along a straight line that connects us to a point B. Okay. And so this is what I mean by this is the type of monotonic increasing stress I'm talking about. So we could then write that sigma ij, the stress during this loading at any given time, is going to be equal to sigma ij, that's at A, plus, then of course just the slope basically, so sigma ij B minus sigma ij A, so that quantity, times some quantity we'll call lambda, which varies in time. We call this equation 2. And the only thing that we require is that sigma ij B will be greater than or equal to sigma ij A, right? Otherwise we don't have an increasing stress. And we also require that lambda be some value in between 0 and 1. Okay, so those restrictions that we give we'll call equation 3. And I'll say also where lambda is an increasing function of time. Okay, when we have this kind of loading, it's referred to as proportional. So this is proportional loading. Right? So it's just thought of as, yes, the stress changes, but the proportions of the stress. So let's say if we had our example of maybe on the x-axis being sigma 1, 1 and the y-axis being sigma 1, 2, the proportions of sigma 1, 1 relative to sigma 1, 2 does not change during the load, okay? So that's what we mean by proportional loading. Okay, we can take the differential of equation 2, okay, and is d sigma ij, which I hope you expect I'm going to plug back into my criteria that d sigma ij, d epsilon ij greater than or equal to 0 for the material we care about, and that's what we're going to do. But let's define d sigma ij for this type of loading. Obviously, the differential of a fixed stress sigma ija is 0, and then we have this constant, which is sigma ij b minus sigma ij a times d lambda, right? That would be the differential. We'll call that equation 4. And then we're going to substitute equation 4 into the original inequality of equation 1. Okay, and when we do that, we end up with that sigma ij b minus sigma ij a d lambda, and then now we have this d epsilon ij is greater than or equal to 0. Call that equation 5. Okay, so now we can make some assumptions. We said that lambda was an increasing function, so d lambda is greater than 0. So if we were to divide by d lambda, this still would be 0 over here, and then we could write, so I'll just say because d lambda is greater than 0, we may write that sigma ij b minus sigma ij a d epsilon ij is also greater than or equal to 0. Okay? Call that equation 6. All right. So now we're going to remember too that lambda itself had a value in between 0 and 1, right? So if we were to, this is essentially 1 multiplying in this constant value times whatever this increment is, so that we could write, so just say note that lambda is somewhere in between 0 and 1. So we can write sigma ij b minus sigma ij a times d epsilon ij. that must be greater than or equal to sigma ijb minus sigma ija now times lambda times d epsilon ij, which is then greater than or equal to 0, right? Because lambda is less than 1, greater than 0, it's going to be less than this quantity and greater than 0, right? Call that equation 7. We know what this quantity is, right? What is that quantity? Well, that quantity, we can write this as sigma ij, which is what we had defined initially, minus sigma ij a, right? So this whole quantity is that. So therefore we can write that now as, so we can now write sigma ij b minus sigma ij a d epsilon ij is greater than or equal to sigma ij minus sigma ij a times d epsilon ij, which is greater than or equal to 0, and we call that equation 8. Okay? Now, I'm going to integrate equation 8 from a to b. So, integrating 8 from a to b. So the first integral, I'm going to integrate, I'm integrating over epsilon, so this is just epsilon ij a, epsilon ij b, now times sigma ij b minus sigma ij a d epsilon ij. That must be greater than or equal to, I'm going to integrate the next piece, integral from epsilon ij a to epsilon ij b times sigma ij minus sigma ij a d epsilon ij going to be greater than or equal to 0. Okay, so what about this side? Well, this value is constant, right? There's no variable there, so we can pull it outside the integral, and so this just becomes the integral from epsilon ija to epsilon ijb of d epsilon ij, which is actually very simple. We can write this then as sigma ij b minus sigma ij a times epsilon ij b minus epsilon ij a. Okay? And then that's going to be greater than or equal to the integral from epsilon ij a epsilon ij b times sigma ij minus sigma ij a d epsilon ij must be greater than or equal to 0. We'll call that equation 9. Okay? Okay, so we've kind of come to a point where we need to think about what we've just done. Okay? First, I want to define the term that's in the integral. So the term, that's the integral from epsilon ija to epsilon ijb of sigma ij minus sigma ija d epsilon ij. That term is called the net stress work. Okay? And what does it represent? It represents, it represents the work done by the stresses in excess of sigma ija. Okay? So we can draw a picture of this. So let's draw our stress strain curve. So there's our strain, epsilon ij. Here's our stress, sigma ij. And let's say we ramp up and then we get our curve that looks something like this. Let's call this value here, let's say that is sigma ija. And let's say some value that's higher is sigma ijb. Okay? So if that's the case, so there intersects our constitutive law there, when this must be then epsilon ij b, And then we can do the same with A. And this is epsilon ij A. Okay, so what the net stress work is it is the area under that curve. So this is the net stress work. Okay? All right. So what does equation 9 tell us? It says that the net stress work is always greater than or equal to 0. We have a sort of a more formal way to say that. So in mechanics speak or in mathematics speak, we're going to say that equation 9 can be restated that the net stress work is what's called positive semi-definite. Right? And all that means is that it's greater than or equal to 0, right? So this value is greater than or equal to 0. Okay? Okay, now I want to give you another definition. The other side is what's called the complementary net stress work. So the complementary net stress work is going to be defined as the integral. Now instead of integrating in d epsilon, we're going to integrate in d sigma, and it's going to be sigma ij a up to sigma ij b of now epsilon ij minus epsilon ij a times d epsilon, times d sigma ij. Okay? So that's the complementary net stress work. And if we want to draw it on this picture up here, it is this area that's above the curve. Right? That would be the complementary net stress work. Okay? So this is complementary. Okay? So what could we say about that term with respect to this type of behavior? So we can actually use equation 9 above, what we just talked about for the net stress work being positive semi-definite, and we can develop restrictions also on the complementary net stress work. Okay, so how do we do that? Well, we actually integrate the network by parts. I don't know, you're probably sitting in this class going, wow, I really forgot a lot of my calculus, and I didn't ever think I would need this again. But so hopefully you remember a little bit about integration by parts. So let's go ahead and just write the net stress work. So that would be the integral epsilon ij a up to epsilon ij b times sigma ij minus sigma ij a d epsilon ij. And if we integrate that by parts, then we would write sigma ij minus sigma ij a times epsilon ij evaluated at point A and B minus the integral now from sigma ij a to sigma ij b times epsilon ij, and then of course the differential of this, the constant goes away, and we're just left with d sigma ij. Okay, so that doesn't quite yet look like our complementary stress work, but we're going to do a little work to get there. If I go ahead and evaluate this, what's sigma ij evaluated at point B? Well, that's just sigma ij b minus sigma ij a, that quantity. And of course, epsilon ij evaluated at B is just epsilon ij b, right? Okay, if I evaluated at A, then this quantity becomes sigma ija, so sigma ija minus sigma ija is 0, so we don't have anything there. And then we're left with this other integral, sigma ija, sigma ijb times epsilon ij d sigma ij. Okay? So now we do a little bit of a trick. We want this term to have to look like epsilon ij minus epsilon ija, right? In order for us to have it be the complementary strain energy, sorry, the complementary network rather. So what we can do is we can simply add and subtract this quantity times epsilon ija, and so we would write this as sigma ij times b minus sigma ij times a times epsilon ijb minus epsilon ij a. Okay, so I've basically subtracted this quantity times this coefficient. I have to add that back on, so I have plus sigma ij b minus sigma ij a times epsilon ij a, right? So I've added and subtracted, so I've added effectively 0, and then I have my minus the integral from sigma ij a up to sigma ijb of epsilon ij d sigma ij. Okay, so let's go ahead and keep on. Let's say that this is now equal to, what does this term look like? Well, this term is actually the integral of epsilon ija integrated for d sigma from sigma ija to sigma ijb, and so we can bring that inside this integral here, and we can write then that sigma ijb minus sigma ija times epsilon ijb minus epsilon ija, and now we have minus the integral from sigma ija up to sigma ijb. Now we have epsilon ij minus epsilon ija times d sigma ij, right? So what we've done is that we have now gotten, this is the net complementary stress work. Okay, so let's go ahead and call this equation 10. And now we substitute 10 into 9, that initial equation we had, the initial inequality we had for our net stress work. So substitute 10 into 9, right? And we end up with, the first side of that was just sigma ij, if you remember, b minus sigma ij a times epsilon ijb minus epsilon ij a is greater than or equal to, now we're going to make our substitution, of equation 10 in here. This is sigma ij b minus sigma ij a times epsilon ij b minus epsilon ij a minus the integral from sigma ij a to sigma ij b epsilon ij minus epsilon ij a, that quantity times d sigma ij. Okay? So what can we do here? Well, obviously this and this are equal, right? This left-hand side is equal to this term. So those actually will cancel. And I'm left with 0 is greater than the negative value of this, or I'm left with integral from sigma ij a to sigma ij b of the quantity epsilon ij minus epsilon ij a times d sigma ij is greater than or equal to 0. Okay? So we can call that equation 11. And we've basically just shown that the complementary net stress work, or the net complementary stress work, is also greater than 0, or in our math terms, positive semi-definite. Okay? So that leads us to our first postulate that we want to propose. So here's our postulate. Okay? For an inelastic material subjected to a monotonic proportional loading, which is going to be given by, right, that sigma ij is going to be equal to sigma ij A plus sigma ij B minus sigma ij A times lambda, and that sigma ij B minus sigma ij A is greater than or equal to 0, and also that lambda is in between 0 and 1 and is increasing. Okay? So for that case, the net stress work and the net complementary stress work are positive semi-definite, right? Which you can just remember is greater than or equal to 0. Okay, so that's our first postulate. We'll use that in terms of evaluating material behavior in future lectures. Okay?